Good morning, everyone. Welcome to today's hearing. Today we're going to hear a presentation by Dr. Barbara Lane on testing materials.
Yes, Mr. Chairman, before Dr. Lane comes in, I was just going to introduce what she was going to cover. She's going to explain the national testing and classification regime, including what is meant by Class 0. She's also going to explain the European testing and classification regime, and also the large-scale testing which occurs under BS 8414 Parts 1 and 2 and classification to BR 135. It will be an oral presentation only and not a question and answer session. And before she starts, I do need to give a trigger warning about the presentation and some of its content. There are included within the presentation some images and videos of fire scenarios, and also included are some images of Grenfell Tower on the night and when on fire, and some images of the damage to Grenfell Tower inside taken afterwards. So it's important to give that trigger warning for anybody who's watching and who would prefer not to see such material.
Thank you very much.
So if I can now invite Dr. Lane to come in to be sworn in and to give her presentation.
Thank you.
On your right hand and repeat after me. I swear by Almighty God.
I swear by Almighty God
that the evidence I shall give.
That the evidence I shall give.
Shall be the truth.
Shall be the truth.
The whole truth.
The whole truth.
And nothing but the truth.
And nothing but the truth.
Thank you very much, Dr. Lane. Good morning. It's nice to see you again.
Thank you.
Yes, Dr. Lane, if you'd like to go ahead and give your presentation.
Okay, thank you.
Thank you very much.
Good morning. Throughout Module 2 of this inquiry, regular reference will be made to the products used to create the new external wall during the Grenfell Tower refurbishment. Various fire performances will be referenced throughout the evidence. Various reaction to fire tests will also be referenced. Phrases such as national classes and national testing, as well as European classes and European testing, will become very familiar in the coming weeks. In my presentation today, I will explain what those classes mean and how they were derived. I will also explain the reaction to fire tests upon which those classes rely. Reaction to fire tests are a particular form of fire test used to characterise the performance of construction products. The approved document B refers to reaction to fire tests, national classifications and European classifications when setting out the performance of products for use in external walls. It is by means of national and European classes, the guidance document states that provisions are made to restrict the combustibility of external walls of high buildings. Also, as stated at section 12.2 in the guidance document, these are the provisions to reduce the surface's susceptibility to ignition from an external source and to reduce the danger from fire spread up the external face of the building. It is critical to understand the difference in definition for each class and the different reaction to fire tests associated with each class. This complexity lies at the heart of accurately communicating external wall performance and fire as presented in section 12 of the approved document B. This is a technically complex subject with many different fire tests, classes and definitions. It means there is a precision needed when communicating the provisions made in the statutory guidance document, and so when considering the external wall products used at Grenfell Tower. In general, my presentation relies exactly on the text provided in the relevant British and European standard. Details most useful to wider activities within the test lab I have omitted, as I do not consider them relevant to the explanations I am giving here today, but they can be found in the reference documents, and I have provided those references on the slides as I progress. As part of my work for this inquiry, with technical assistance from Tom Parker, who is here with me today, I've carried out research into the history of these tests, classes and their definitions. I have also analysed how they have been presented over the years in the building regulations and the approved documents. The statutory guidance document, approved document B 2013, was approved and issued by the Secretary of State for the purpose of providing practical guidance with respect to the requirements of the Building Regulations 2010 for England and Wales. My presentation focuses on this version and earlier versions. It does not deal at all with any changes that have occurred since the night of the Grenfell fire. I have structured the presentation today into 4 main sections. In doing this, I will therefore explain in detail the 8 reaction to fire tests referred to from within ADB, as well as the 2 larger scale cladding tests referenced there also. In each section, I will show various images and movies, and Tom Parker will also present the 2 scale models we built at Arup of the specimens used in the 8 reaction to fire tests. We do not have the large cladding test samples due to their scale, and so I will show images and movies of those cladding tests only. After I explain some classic fire behaviours and how those behaviours were observed at Grenfell, I will then explain the 4 national reaction to fire tests and the definitions then used when setting out the national classes relied upon within approved document B. I will show how these definitions have been relied on since 1965 and significant changes made to those definitions in that time. In section 2, I will explain the 4 European reaction to fire tests, the European classification criteria, and the resulting European classes relied upon within approved document B. I will explain the importance placed on the relevant field of application for products tested using European reaction to fire tests. I will set out how European classes are referred to from approved document B, and then address some issues regarding equivalency when comparing the European classes with the national classes. Finally, in section 3, I will provide a summary description of both the performance criteria given in the BRE report 135, which considers cladding systems, not individual products. I will also explain the full-scale tests and data produced from the fire tests called British Standard 8414, Parts 1 and 2. The data obtained from these tests is assessed using BR 135. Then a classification report can be produced for the cladding system tested. I will explain earlier versions of these publications also and how they have been referenced from the statutory guidance documents over time. The first thing I will present to you today relates to the basic science of fire in a compartment or room. A fire is characterised in a series of discrete stages for the purposes of scientific calculations and understanding. And it is very useful to understand those stages and how they relate to the reaction to fire tests I'm setting out for you today. I thought it was useful to explain in brief how fires behave in compartments or rooms because of what is stated in British Standard 476 Part 10. British Standard 476 contains a series of fire tests, 4 of which I'll be explaining in detail today. They are the 4 national reaction to fire tests. Part 10 of this standard examines the principles, objectives and outputs of fire testing in the BS 476 series, offering guidance on selecting appropriate test methods. It states, Reaction to fire tests are used to characterise the performance of construction products or materials in terms of their contribution to the initiation and growth stages of a fire leading up to flashover. The underlying philosophy is that if a fire starts, its rate of growth should be such that there is adequate time for the building occupants to escape to a place of safety without being injured. I will summarise the discrete stages of a fully developed fire in a room or compartment in the next few slides. This is a highly complex area of fire science, and I make no attempt to cover the subject in depth. My intention is to provide an overview of the classic behaviours upon which fire science relies. After ignition, the fire is typically initially small. Here at the 3-second photo from an experiment carried out in the USA by NIST, it is burning with visible flame. It then grows in size as shown at the 18-second image and the 32-second image. This is the result of flame spread over the item first ignited and spreading to nearby objects if sufficient oxygen is available. At some point, due to the enclosure surrounding this localised fire and the available ventilation to that fire within the enclosure, those parameters influence further fire development. And so the power of the fire increases with time. This graph represents the course of a well-ventilated compartment fire, expressed as the rate of heat release as a function of time within that compartment. The internal compartment fire shown here is mostly divided into 3 substantial phases after ignition, but also incorporating a short transition phase called flashover. So looking at the graph from left to right, after ignition, which occurs when fuel, energy and oxygen are available in sufficient quantities to initiate combustion, then we see the growth period on the graph. This is flame and combustion leading to the ignition of additional fuel if sufficient oxygen is available. Then flashover can occur. During the growth phase of a fire, the thermal energy within the room increases to a point at which there is rapid ignition of the remaining unburned fuels, provided there is sufficient oxygen. Afterwards is the fully developed fire phase. Now the energy release is at its greatest in the room or compartment. Then decay, as the fully developed flame starts to run out of fuel or oxygen. Flashover is therefore an important indicator of the onset of a fully developed fire and only occurs if there is sufficient air. I recommend the Drysdale reference for a more detailed understanding. Please watch this short video of an internal compartment fire growing. Yeah, it doesn't seem to be. Just 1 second. I don't think it's the. I think I'll have to move on. It was meant to be connected to the internet. It's from the helmet cam of a firefighter in a room as a fire grows rapidly. I wonder, is there a way of getting the movie to work? Be very helpful. Yeah. Yeah, here we go. Thank you. Watch how quickly the fire takes hold of the stacked timber in the corner and forms a smoke and flame layer at the ceiling within the room. The flame spreads across the ceiling, seeking out ventilation along the corridor. The smoke and flame layer build down to floor level. This room contains very little combustible material, and so a prolonged, fully developed fire cannot occur. So back to BS 476 Part 10. It helpfully sets out what tests in the 476 series are relevant in the context of the classic room fire stages I have just summarised for you. It places the reaction to fire tests as relevant to the period of time before flashover. Flashover is marked with an X on this graph. And the reaction to fire test references can be observed in the red marked area underneath flashover. The reaction to fire tests referred to for the external wall in the statutory guidance document are therefore associated with pre-flashover or early stage internal room fire growth. There are other tests referenced by the British Standard for the post-flashover condition after the X marked on the graph here. But what of reality as we saw at Grenfell and have seen elsewhere? I will now use some photos from the Grenfell fire for the next 5 slides. We know that the fire spread from the external wall back into many flats that night, then caused a fully developed fire, consuming everything in the room, the result of which I have shown in the photo here, and the fire curve representation of this fully developed fire is marked in red. We know there was a prolonged decay phase in that it occurred at different times in all different parts of the tower. In this phase, the rate of burning is diminishing, the fuel is depleted of volatiles, the gas is formed when something is heated in a fire. Flaming eventually ceases, and this stage leaves a mass of glowing embers. This state may remain for long periods, and there can even remain high localised temperatures. Again, this behaviour is concerned with the performance inside the building. But we know too that there were different types of internal fire. There were localised fires that night, of a scale as I presented in the earlier NIST experiment and shown on the left here. And as seen, for example, at flat 16, the image here showing the internal localised fire. But in this photo, one can also see some external flaming, despite this room fire still being in its early growth phase only, represented by the red area on the graph. And we know too that flashover did occur in many compartments, and so fully developed fires were observed throughout the night. The scale of these post-flashover fires, or fully developed fires, are much larger and their consequences more severe than the pre-flashover conditions. Flames may emerge from ventilation openings such as windows. The threat to neighbouring compartments or adjacent buildings is then at its highest. The fire can spread through any internal openings, such as doors or unsealed openings in the compartment. So this is the stage of the fire when damage to structure becomes a concern. It is the time of highest life safety risk to firefighters, and it is too late for anyone who has not already left the compartment. But what about the external wall fire scenarios? We know that early in the night at Grenfell, and shown here at 1:26, an external fire event in the external wall had occurred. In the beginning, it was localised and external to one compartment, and then rapidly spread externally up the tower. I hope, Mr. Chairman, the panel can consider the following point. This external scenario, either when small or large, was separate to the internal room fire. This internal fire behaviour characterised by the temperature time graphs I've shown you today. The external fire scenario is not the same as the early stage fire behaviour in a room. The external fire is not controlled by the room enclosure or room ventilation phenomena that cause classic room fire behaviours. Yet the statutory guidance document relies on reaction to fire tests for internal rooms. BS 476 Part 10 states they are used to characterise the performance of construction products in terms of their contribution to the growth stages of a fire inside a room leading up to flashover only. But pre- and post-flashover are not external fire phenomena. They are internal compartment phenomena. But every reaction to fire test I explained today was apparently created to characterise performance in an internal room fire. The tests are not deemed to be representative of external fire behaviour if one relies on the British Standard explanation in itself. It will be useful to understand why, therefore, they form such a fundamental part of the external wall fire performance set out in Approved Document B. Throughout today, you will also hear what those tests do demonstrate regarding the fire performance of materials and products, and this is to assist you in your deliberations. There are 8 reaction to fire tests referenced within approved document B. There are 4 national test standards and 4 European test standards. The national tests from the British Standard 476 series are parts 4, 6, 7 and 11. The European tests are not in a series and are 4 distinct tests: BSEN 13823, BSEN ISO 1716 and 11925 Part 2, and BSEN 1182, where EN means European norms and ISO means International Standards Organisation. I will now explain the setup for each one of these tests, how the test is then done, and how the results from each test is then used and relied upon to classify the performance of construction products and materials. The 4 national reaction to fire tests are part of BS 476 series, as I said. Each part addresses a different element of contribution in a fire. Part 4 is a test of non-combustibility for materials. Part 6 is a test of fire propagation for products. This means a comparative measure of the contribution to the growth of fire of a combustible material. Part 7 is a test to classify the surface spread of flame of a product. And Part 11 is a test to assess the heat emission from materials. British standards are issued by the British Standards Institute. There are specific subcommittees made up of industry and governmental bodies that draft the standards. The second page of the standards typically lists the parties involved in drafting the standard. On screen now are examples taken from Part 4 and Part 6. First, I will explain Part 4, the non-combustibility test for materials. There has been one version of Part 4 published, and this was in 1970, with 2 further amendments made in 1978 and 1983. Information was added to the foreword in 2014. The test apparatus for the Part 4 tests consists of an electric furnace which is switched on until the furnace temperature reaches a constant 750 degrees Celsius for 10 minutes prior to the test. A cuboid sample is placed in this furnace. The furnace temperature is measured by a thermocouple, positioned so that its hot junction is 10 millimetres from the wall of the furnace and at mid-height of the specimen. A thermocouple is a device for measuring temperature. A second thermocouple is placed in the centre of the specimen, inserted from the top. This shielded thermocouple shall maintain contact with the material at the bottom of the hole, drilled down halfway into the specimen. The image on screen shows a cross-section through the furnace. The key thing to observe here is that the heat is provided by running electricity through wire coils wrapped around a central tube made of alumina refractory material. No direct flame impingement occurs in this test. 3 specimens are prepared, each side a length of 40 millimetres with a height of 50 millimetres. My colleague Tom is now holding up an exact replica of the size of the Part 4 specimen. One complete test consists of testing 3 specimens, each specimen tested separately in the furnace. The specimen is placed in the specimen holder, which is shown in the image on the left. This holder is 100 millimetres high. If the thickness of the material is less than the height required of 50 millimetres, each specimen must then be made of a sufficient number of layers to achieve this thickness. These layers should occupy a horizontal position in the specimen holder and held together firmly without compression of the specimen by steel wires to prevent air gaps. For composite materials of a thickness such that an integral number of layers cannot be put together to give the specific size, the thickness of the different components should be adjusted so their proportions remain the same as the original specimen. If either of these options cannot be followed, the test must be performed on the individual component layers of the material and reported accordingly. No Part 4 test report has been submitted to the inquiry to date, so I cannot confirm what option is typically used in practice for products associated with Grenfell Tower. I will now present a video of the test procedure. Okay. For a tested material to be considered non-combustible by means of this test, none of the three specimens during the test must either cause the temperature reading from either of the two thermocouples to rise by 50 degrees Celsius or more above the initial furnace temperature, or be observed to flame continuously for 10 seconds or more inside the furnace. Otherwise, the material shall be deemed combustible. The requirements of the test report are shown here, with a single designation to be provided. That concludes my description of the Part 4 non-combustibility test for materials. The second national reaction to fire test I will explain is Part 11, which is the method for assessing the heat emission for building materials. This was current during the primary refurbishment, and it is the national test for materials of limited combustibility, the performance for insulation in external walls. This standard has had no amendments, and again, information was added to the foreword in 2014. The Fire Vocabulary British Standard, BS 4422, defines fire as the process of combustion characterised by the emission of heat and effluent accompanied by smoke, flame, or glowing. So the purpose of this test is to assess the heat emission. It is done by measuring the temperature rise from the specimen as a result of being in a furnace, as well as the specimen mass loss and any observed flaming during the test. The test apparatus in this heat emission test is similar to that used in the non-combustibility test, with a notable exception being the design of the specimen holder. Other amendments include a prescribed design for the electrical furnace windings. A mirror is proposed to allow the operator to observe flaming easier. The apparatus also includes an additional support to the specimen insertion device. Part 11 also consists of an electric furnace with the power input to the furnace such that the temperature measured by the furnace thermocouple is stabilised at 750 degrees Celsius. This specimen holder has a circular base to accommodate cylindrical test specimens. The furnace thermocouple is to be located 10 millimetres from the furnace tube wall and at a height corresponding to the midpoint of the furnace tube. The specimen thermocouple is positioned at the geometric centre of the specimen. A third thermocouple is also added to allow a horizontal contact with the interior of the furnace wall. The procedure for Part 11 is similar to the non-combustibility test I've just explained, such that temperature measurements and flame observations are also taken. However, the duration of this test can be up to 120 minutes, and the mass of the sample is obtained before the tests. This time 5 specimens must be prepared. Each one a cylinder 45 millimetres in diameter and 50 millimetres in height. My colleague Tom is now showing you an exact replica of a Part 11 test specimen. The specimen is then put into the holder, as shown in the image on the left, and again a thermocouple is inserted through a 2 millimetre drilled hole at the top of the specimen. Again, specimens must meet the minimum height required for the test specimen of 50 millimetres. For a material with a normal thickness greater than 50 mil, it should be reduced. If the thickness of the material is less than 50 mil, the right height should be made using a sufficient number of layers of the material or adjusting the material thickness. The video on screen now shows this test procedure. Following the test, 2 results are calculated. First, the furnace temperature rise is calculated as the maximum furnace temperature minus the final furnace temperature. Secondly, the specimen temperature rise is calculated by taking the maximum specimen temperature minus the final specimen temperature. This is calculated for each of the 5 specimens and an average value is obtained. The average duration of total sustained flaming is also calculated for the 5 samples and recorded in the report. The operator is also required to calculate and record the density, calculate the arithmetic mean of the density, calculate and record the mass loss of each individual specimen, calculate the arithmetic mean of the mass loss of the specimens tested as a percentage. These 5 measurements must be recorded in the fire test report. It is a requirement of the test report that the following text is stated. The results relate only to the behaviour of the specimens of the material under the particular conditions of the test. The results obtained on an individual material used in a combination should not be construed as reflecting the performance of the material combination as a whole, which may be influenced by the mechanism of combining the individual materials together, such as with adhesives. The results are not intended to be the sole criterion for assessing the potential fire hazard of the material in use. This is the important test for materials of limited combustibility, noting no evidence of such a test has been submitted to the inquiry at this time. The third national test I will explain is BS 476 Part 6. This is the method of test for fire propagation of products. It is this test combined with a second test, BS 476 Part 7, which taken together form the basis of Class Naught, about which you have heard and will continue to hear a lot about. The Fire Propagation Index is defined in the Fire Vocabulary British Standard, BS 4422, as a comparative measure of the contribution to the growth of fire of a combustible material. This is a very different kind of reaction to fire test to those I've shown you so far today, and Part 6 relies on a different form of test apparatus. It was first published in 1968. Since then, 3 further versions were published, with the most recent dated 2009. In 2014, this too had a change made to its foreword. The version relevant to the Grenfell Tower refurbishment was the 2009 version. The scope section of Part 6 states, this part of BS 476 specifies a method of test, the result being expressed as a fire propagation index, that provides a comparative measure of the contribution to the growth of fire made by an essentially flat material, composite or assembly. It is primarily intended for the assessment of the performance of internal wall and ceiling linings. The test apparatus comprises a combustion chamber with a specimen holder that is fixed onto the front face. The combustion chamber contains a horizontal gas burner tube and 2 electrical heating elements, and is surmounted by a removable steel chimney and cowl. The specimen holder is made from calcium silicate board, having the same dry density and properties as that of the walls of the combustion chamber. The holder is recessed to take a specimen of area 225 mm by 225 mm, with a recessed depth of 12.5, 25 or 50 millimetres, depending on the specimen to be tested. A non-combustible compressible gasket 1 millimetre thick is provided for interposing between the specimen holder and the combustion chamber to assist in obtaining an adequate seal. On screen now is a close-up of the combustion chamber showing the 3 heat sources, 2 electric heating elements and a gas burner as shown. The internal dimensions of the combustion chamber are 190 millimetres by 190 millimetres and a depth of 90 millimetres. I show a cross-section on the next slide. At the top of the combustion chamber is a chimney where hot gases can leave the chamber. As indicated by the dashed arrow, the combustion chamber is 90 millimetres deep. It is useful to understand the depth of the specimen holder, which is marked green and attached to the front face of the chamber. The image on screen shows the specimen being held up in front of the opening to the combustion chamber. The opening to the combustion chamber recess is slightly smaller than the green specimen on the screen. Each specimen is square and measures 225 by 225, as I said. My colleague Tom is now holding up an example of the Part 6 specimen. Whilst the sample is of dimension 225 millimetres, the opening in the combustion chamber is 190 by 190 millimetres. The result of this is that a boundary around the edge of the sample is not directly exposed to the heat from the electric heaters and gas burner. Products with a normal thickness of 50 millimetres or less are tested at full thickness. For products of normal thickness greater than 50 mil, the specimen is obtained by cutting away the unexposed face of the product to reduce the thickness to the required 50 mil. It is stated in the standard, where the product is normally used as a freestanding sheet, then an airspace should be provided at the back of the product by testing over non-combustible perimeter battens. Where the specimen is backed by an air gap, ensure that the perimeter of the specimen will not permit flame to penetrate into the cavity. Similarly, where a flame retardant coating is applied to a surface, the edge detail shall be such as to prevent ignition of the underlying layers. This detailed information in this British standard emphasises the importance of preventing heat transfer through the cut edges of the sample, therefore. This is to make sure the front face heating occurs only, and that the fire propagation index calculated is as a result of this front face heating regime only. Part 6 also makes a clear statement on the influence of underlying layers on the performance of the assembly when being tested in this combustion chamber. It advises that increasing the thermal capacity of the underlying construction increases the heat sink effect, and this may delay ignition of the exposed surface. It states that care should be taken to ensure the result obtained on any assembly is relevant to its use in practice. Several options are then provided with regard to the preparation of the test specimen, and if it can rest directly on the specimen holder, or if it requires a substrate between it and the specimen holder. And these are all shown on the screen here. Prior to the test, the specimen holder is then firmly fixed in place as shown on screen. During the test, both the gas burner and the two electric heating elements are used, which I will explain later. The temperature output from the thermocouples of the flue gases in the chimney is measured throughout the test, with specific temperature measurements noted at set time intervals, which I will also describe later. The image on screen now shows the rear of the apparatus. This features an observation window and an air inlet below. Visual observations are made during the test through the window. These must include intumescence or deformation or spalling of the specimen that tends to block the burner ports so the required gas input cannot be maintained, or melting or slumping of the specimen that results in material escaping from the air inlet or being confined to the recess of the specimen holder where it is not exposed to the heating conditions. Airflow through the apparatus being restricted owing to obstruction of the inlet port by fallen material or by soot accumulation in the chimney. Occurrence of any of the above phenomena shall deem the test on that specimen to be invalid. This test consists of data measured from two different materials. As well as the specimen to be tested, the test also requires a specimen of calcium silicate to be prepared. Calcium silicate is a non-combustible material, and Tom is now holding up a piece of that board for reference. In its board form, it is used in the test combustion chamber as a benchmark, and the data from the test specimen is then compared to the data obtained when the calcium silicate board is tested first. Only one calcium silicate specimen is required, however, at least 3 of the material specimens must be tested. I will now present a video of this test procedure. the output from the 2 thermocouples located in the chimney is recorded at some specific intervals we need to discuss. At 0.5 minute intervals up to and including 3 minutes from the time at which the gas was ignited, and this is then converted to a parameter called S1. At 1 minute intervals up to and including 10 minutes from the time at which the gas was ignited, and this is then converted to a parameter called S2. 2 minute intervals up to and including 20 minutes from the time at which the gas was ignited, which is then converted to a parameter called S3. All the visual observations should be recorded during the test as observed through the window, as I have already explained. The ultimate output of this Part 6 test is a parameter called the Fire Propagation Index I and sub-indices little I1, little I2 and little I3. These parameters are directly referenced by Approved Document B, as shown on the screen as part of the fire definition of Class 0. It is critical people understand the Fire Propagation Index and the sub-indices only come from BS 476 Part 6. I will now explain how the indices are derived. Regarding the sub-indices S1, S2 and S3, I have provided the formulae to calculate them circled in the green box, which uses the measured temperatures shown on the screen now. These S values are then averaged and used to calculate little I1, 2 and 3, as shown in the orange box below. Sub-index little I1, sub-index little I2 and sub-index little I3 are then summed to obtain the index of overall performance I of the product. Please just remember that the only measurement taken as part of this test methodology is the temperature from the thermocouples within the chimney at the top of the combustion chamber at set time periods, which are then converted to temperatures. The standard specifies the required contents of the test report. I particularly note the report must state details of the form in which the specimens were tested, material, composite or assembly, together with specimen thickness and, where appropriate, orientation, the backing material and the face or faces subjected to the test, and whether the material was tested in a modified form. The statement that the suffix R to the fire propagation index indicates that the results should be treated with caution. And the test report must contain the statement, again, the test results relate only to the behaviour of the test specimens of the product under the particular conditions of test. They are not intended to be the sole criterion for assessing the potential fire hazard of the product in use. The test setup is designed to prevent heating through the cut edges of the test specimen. For a composite material, therefore, such as ACM, it would mean the outer aluminium surface is heated first, and the products of combustion from any other material behind it, should they receive sufficient heat, together may cause a temperature rise in the chimney. This is why it is important to understand how much heat energy is applied to the sample in this standard test, which has a duration of 20 minutes. I have found some historic work regarding this heating dose received on the surface of the specimen tested in Part 6. In 1968, the BRE issued Fire Note 710, titled The Fire Propagation Test as a Measure of the Fire Hazard of a Ceiling Lining. As stated in the note, part of the study involved measuring the rate of heat transfer to a specimen in the fire propagation test. On screen now, I've shown some text explaining the heat exposure measurements produced in this paper. This is for background information only, because the key information I want to present is the graph referenced within this test. within this text. This is figure 1 from fire note 710, and it shows the gross heat flow, the heat flux, received at and on the surface of the asbestos wood sample used in the test. The paper, for any fire scientists listening, defined the gross heat flow as the algebraic sum of the rates of heat transfer into the specimen by conduction, from the surface by radiation, and from the surface by convection. So to understand if a similar heat received on a surface of a different type of specimen as a result of this scale of heating is then sufficient to ignite the specimen being tested, I present the following. I have compared the received heat measured in this paper on asbestos wood, shown by the dark blue line on the screen. And I have compared it with critical heat flux values associated with the materials used in the external wall of Grenfell Tower. I have done this purely to give a sense of scale of the heating regime within the combustion chamber only. Fire note 710 states the gross heat transfer rates will be higher for good insulators, although they will be of the same order and will vary with time in much the same way. So it is reasonable in trying to understand the scale of heat applied to the surface of materials in the Part 6 test to rely on the dark blue line for comparison. I have used dashed lines to overmark the graph with values of typical critical heat fluxes needed for the piloted ignition of the materials. This is the ignition that occurs when a flame is impinged on the specimen. I have provided those classic and typical values for PIR foam and phenolic foam, polyethylene and wood. Therefore, with the heating dose from the Part 6 test, the applied heat flux to the sample made of wood, the wood would be expected to ignite between 3 and 4 minutes. For polyethylene, this would be after 4 minutes. PIR would ignite between 4 and 5 minutes, and phenolic foam after 8 minutes. The Part 6 test is a total duration of 20 minutes. I note that the melting point of polyethylene is approximately 130 degrees Celsius, whereas the melting point of aluminium is over 660 degrees Celsius. Based on the test reports submitted to the inquiry, when ACM panels are tested in this apparatus, the aluminium can sometimes act as a protection to the polyethylene, protecting it from direct flame exposure, and therefore the polyethylene sometimes melts and flows away rather than ignites within the panel during the test. If it does not ignite, the temperatures measured in the chimney are lower. I have now added to this comparison graph the time period when the temperatures forming the index S1 are actually calculated. During this period, please note the heat exposure to the specimen is actually less than that required to ignite wood or polyethylene. I have also marked the time periods when the temperatures forming the sub-index S2 and S3, forming little s2 and little s3 are also calculated. To sum up, the Part 6 test is the fire propagation index test and is based on the temperatures measured in the chimney. The product tested is then assigned little s1, little s2 and a little s3 sub-index. These are averaged across 3 tests to obtain the sub-indices little i1, 2 and 3. The sub-index little i1 is therefore an average of measurements taken during the first few minutes of the test only, when the heating dose is relatively low. I have shown how little i1 is referred to in the ADB on the screen marked in purple. There, the ADB also refers to a fire propagation index I. This is the overall index and is based on the heating dose received over the 20-minute period. Composites can be tested However, when they are tested, the specimen is arranged to ensure the front face heating of the specimen only. The fourth and final national reaction to fire test is BS 476 Part 7. Method of test to determine the classification of the surface spread of flame of products. This must be combined with Part 6, as I have just explained, when understanding the derivation of Class 0 as set out in the ADB. I want to stress that Class 0 is not simply a surface spread of flame test, as so commonly stated. Only the Part 7 test on its own is, and there is no national class that relies solely on Part 7. Class 0 is defined on the basis of the two tests, and this is a critical distinction that must be incorporated in any evidence given to the inquiry regarding Class 0. There have been 3 versions of Part 7 published, first in 1971, with 2 further revisions in 1987 and 1997, and a change to the foreword only in 2014. The foreword section of Part 7 states, the test takes account of the combined effects of factors such as ignition characteristics and the extent to which the flame spreads over the surface of the product under opposed flow conditions. The influence of any underlying materials on these factors in relation to their ability to influence the rate of fire growth is also taken into account. The test result is a function of the distance and rate of the lateral spread of flame, and this is classified according to performance as classes 1 to 4. The scope section of Part 7 states, this part provides data suitable for comparing the end-use performances of essentially flat materials, composites or assemblies, which are used primarily as the exposed surfaces of walls or ceilings. The scale of apparatus used in the Part 7 test is very different to the other 3 national reaction to fire tests, and relatively speaking is a much larger test. However, it is still important to note how much smaller this sample size is when considering the scale of a cladding panel used in construction. I will show an image to help understand this later. The Part 7 apparatus consists of an 850mm by 850mm radiation panel mounted vertically in a surround and supported on a framework. The specimen holder protrudes perpendicular from the radiating surface. A small pilot flame tube is also provided as part of the apparatus. This is the largest specimen required for a national reaction to fire test, and each specimen is a rectangle measuring 885 millimetres long and is 270 millimetres in height. Tom is now holding up an exact replica of the Part 7 sample. When the product is of insufficient size to allow the specimen size to be achieved in width or length, it is permissible for small pieces of the product to be placed adjacent to each other to obtain the required dimension, providing that an essentially flat surface can be achieved. And it is considered in the test standard that such a procedure does not have any influence on the surface spread of flame, but the use of such specimens shall be reported. The specimen holder comprises a water-cooled steel frame with water-cooled faceplates. The faceplates overlap the specimens by 20 millimetres on their top and bottom edges and over the vertical edge adjacent to the radiation panel. A spring-loaded clamp is positioned to clamp the specimen against the water-cooled faceplates. The water supplied to the specimen holder is such that the maximum temperature does not exceed 35 degrees Celsius at the outlet from the specimen holder. Specimens are tested at full thickness, so long as they fit into the test frame. Where a material is more than 50 millimetres, it is cut down from the unexposed side to allow it to fit. In the test position, the specimen holder assembly is located at 90 degrees to the face of the radiation panel. The height of the specimen holder the height of the specimen holder is such that the horizontal reference line marked on the specimen and shown on the screen here is brought to the mid-height of the radiation panel. The specimen holder is hinged to allow it to be swung horizontally away from the face of the radiation panel between tests. To assist with interpreting the results, the specimen is marked with reference lines before it is mounted into the test rig, and these lines are at set distances, as shown on the green face of the specimen on this slide. The Part 7 standard sets out how the exposed face of each specimen shall be marked in detail on its surface, the reference line with a reference line along its length and 95 millimetres above its bottom edge. To assist in the observation of flame travel, the specimen shall be marked at intervals along its length with lines normal to the reference line and at intervals shown in Figure 7 of the standard, which is on screen now. The 4 vertical lines that run full height are the classification limit distances along the sample for Class 1, Class 2, Class 3 and Class 4. However, there are a number of other requirements for the specimen, which I will briefly run through. A minimum of 6 and a maximum of 9 test specimens shall be provided, and they shall be representative of the exposed surface of the product. The product shall be tested on that face which is normally exposed in practice, taking account of the following. If it is possible for either or both of the faces to be exposed in use, then if the faces are different or if the core of those faces is asymmetrical, both faces shall be tested. If the face of the product contains a surface irregularity that is specifically directional, for example corrugations, the product shall be tested in both orientations. If the exposed face contains distinct areas of different surface finish or texture, then the appropriate number of specimens shall be provided for each distinct area of such finish or texture. All specimens shall be tested at full thickness or cut away, as I explained earlier. When the product is a thin film, it shall be applied to an appropriate substrate using a method and application rate recommended by the manufacturer. The lab shall determine whether a product incorporates a thin film on its surface and shall note if this is the case. When the product is a material or composite, which would normally be attached to a substrate, it shall be tested in conjunction with the appropriate substrate, also using the fixing technique recommended by the manufacturer. Please note the significance that this standard makes to the effect of the underlying substrate, and the reader is referred to Appendix B of Part 7 for more information. Part 7 also provides a clear explanation regarding the impact of any underlying construction on the ignition performance of the surface. This test standard again provides rules on how the sample should be tested as a result. I will now explain the heating apparatus. It essentially consists of a radiation panel mounted vertically in a surround and supported on a framework so that the centre of the panel is 1.25 metres above floor level. The radiation panel shall be supplied with a gas-air mixture. The radiation panel is 850 ml by 850 ml square, designed to give efficient combustion of the air-gas-air mixture with no flaming occurring on the face of the panel under operational conditions. The radiation panel shall be fitted with a refractory concrete surround. This surround shall project from the face of the radiation panel on its 4 edges by 50 millimetres. Any small gaps between the surround and the radiation panel shall be tightly packed with a flexible, non-combustible insulating material. A separate small pilot flame is also provided in addition to the radiant heat panel and immediately adjacent to the test specimen. This pilot burner shall consist of a steel tube with an internal diameter of nominal value 3 millimetres and an external diameter of nominal value 6.4 millimetres. The burner shall be designed in such a way that with the specimen in the test position, the centre of the burner is positioned exactly as set out in the standard, which I have reproduced here. The video on screen now shows this test procedure. So do you mind if I just try and get the video to work? Yeah. Oh yeah, thank you. Apologies. Throughout the test, it is required to carefully observe the behaviour of the product and make a note of the following phenomena: flashing, transitory flaming. Observe and note other phenomena such as debris falling away from the specimen and whether it is flaming or not, any intumescence or deformation of the specimen. These additional observations do not influence the classification of surface spread of flame. Part 7 sets out 4 classifications based on the spread of flame at 1.5 minutes and the final flame spread after 10 minutes. These are Class 1, Class 2, Class 3 and Class 4, and the limits for each are on screen now. I also note that it is stated that this statement must be included in the test report. Again, the test results relate only to the behaviour of the test specimens of the product under the particular conditions of test. They are not intended to be the sole criterion for assessing the potential fire hazard of the product in use. The inquiry panel should consider that only one of these 4 tests actually measures the rate of flame spread across a specimen, and then the purpose of that test was to measure horizontal spread stated for along walls and ceilings. I'm just going to do about 2 more slides. Finally, I want to explain what extending the field of application means. Again, a phrase that will be used over the coming months when referencing test reports and test standards. As I've shown, each test report for the National Reaction to Fire tests must contain specific information, including the limits of what was physically tested. Part 10, the Guide to the Principles of Fire Testing and Their Outputs, states at paragraph 5.3, within the field of reaction to fire, direct field of application is the application of the test results for a material or product in accordance with the details of how they are tested. Specifically, this means that the mounting and fixing arrangement used in the test method is applied directly to the use of material or product in real end-use conditions. Any variation in the physical properties or thickness of material or product in the end-use application, or variations in the mounting and fixing arrangements, should be either quantitatively determined through a carefully designed test programme, or in some cases be the subject of an assessment or expert judgment by an expert. I am aware of one British standard that gives guidance on the application and extension of results, but this focuses particularly on fire resistance tests, not reaction to fire tests. There is also an industry document issued by the Passive Fire Protection Federation titled Guide to Undertaking Assessments in lieu of Fire Tests. This again sets out guidance on assessing the fire resistance performance of products and systems in lieu of undertaking further British national fire tests. Both documents make passing references only to the reaction to fire tests. Within the industry document, it states on page 4, examples of complex assessments are interpolation, extrapolation of a range of test data to cover the reaction to fire performance of a different thickness of a product. I have not found any other publications for reaction to fire tests relevant at the time of works on Grenfell Tower. However, one extended field of application report for a national reaction to fire test has been submitted to the inquiry. This was done by Exova Warrington Fire on behalf of Kingspan. This was an assessment of the ability of a range of foil-faced polyisocyanurate insulation board materials to comply with the requirements of Class 1 when tested in accordance with Part 7. No analysis is presented within this report, just a statement. No such field of application extensions have been submitted to the inquiry for cladding panels at this time. I've provided my opinion on how the BBA relied on a limited number of tests to issue a BBA certificate for cladding panels at length in my Phase 1 report. I would like now, if possible, to take a short break, please.
Yes, well, that's a very convenient moment. Thank you very much. We'll break until 11:30. Would that be suitable?
Yes, please. Yes,
Right.
thank you.
Thank you. Past 11 then, please. Yes, would you ask Dr. Lane to come back in, please? Thank you. Yes, Dr. Lane. Well, when you're ready to carry on, we're
Yes.
on agog.
Yes.
Thank you.
I will now explain all the national classes and their relationship with these 4 tests. So the first important point is there is no overarching British standard for the classification of products and materials to the national reaction to fire test regime. There is in Europe, which we will discuss in the next section of this presentation. Instead, the national classes rely on fire definitions by means of text in the statutory guidance document B only. The relevant definitions are non-combustible, limited combustibility, class 1 to 4, index I and sub-index little I1 and class 0. These specific fire definitions were provided within Approved Document B 2013. Section 12, the external wall construction, refers to these definitions both in the main text and in the text written on diagram 40, also part of section 12. I will go through this in detail in the next few slides. It is necessary to read Appendix A of Approved Document B to understand the fire definitions. In Table A6 of Appendix A, it explains the use and definitions of non-combustible materials. In Table A7, it explains the use and definitions of materials of limited combustibility. Class 0 is defined separately in paragraph 13 of Appendix A, and Class 1 is referred to at paragraph 13 of Appendix A also. The Fire Propagation Index I and the sub-index little I1, as calculated in the Part 6 test, are referred to at paragraph 12 and paragraph 13 of Appendix A only. So knowledge of all these classes and indices is essential, as well as knowledge of the non-combustible and limited combustibility definitions. And I will now present each of these definitions in turn. Non-combustible is defined in Table A6 of Approved Document B. There are 2 definitions for non-combustible provided, as you can see highlighted on the screen now. Each relies on either the national reaction to fire test data from Part 11 or from Part 4. These are the national class for non-combustible materials. Paragraph D, the lower box marked here, states that products classified as non-combustible under Part 4 are non-combustible for the purposes of this guidance. The other method referred to in Table A6 is any material tested to BS 476 Part 11, the method for assessing the heat emission from building materials, as shown in the upper blue box here. Tom is holding up both samples again now as a reminder. The Part 11 test standard itself does not provide any limits on temperature rise or duration of flaming. Instead, these are set out in Appendix A only at point A as marked in the upper blue box. There, Table A6 states that the material, when tested to Part 11, does not flame nor cause any rise in temperature on either the specimen or furnace thermocouple. This is the national class for non-combustible also. The table on screen compares the 2 limits set for the national class non-combustible using Table A6 of Approved Document 2013. So one can either do a Part 4 test or a Part 11 test. All results must have been recorded as 0 if one relies on Part 11. The second fire definition provided in approved document B is in Table A7, use and definitions of materials of limited combustibility. This is a key definition regarding the products used on Grenfell, as the insulation material in the external wall should have been a material of limited combustibility. You can see in paragraph A that any material defined as non-combustible will also satisfy the national class for limited combustibility too. The primary test that can be done to demonstrate limited combustibility using national test standards is Part 11. Density limits are set, as well as flame and temperature rise limits. I have drawn out the text on the right-hand side of the screen. The column on the left-hand side provides references to specific sections of approved document B where limited combustibility is referenced with respect to the situations where such materials should be used. The references as shown in row 8 of the table apply only to insulation used as part of an external wall. It is critical to understand the explicit reference to insulation in the external wall made in this table A7. The definition of a material of limited combustibility sets out not just temperature and flaming limits, but also makes a distinction regarding the density of the insulation material. If the material density is more than 300 kilograms per meters cubed, the limit on specimen furnace temperature rise is 20 degrees C, with 0 seconds of flaming to have been observed in the Part 11 test. If the material is of density less than 300 kilograms per meters cubed, the limits for observed flaming increase to a total of 10 seconds over the course of the whole test. The limit on specimen furnace temperature rise is slightly higher at 25 degrees Celsius, with an additional limit set on specimen thermocouple temperature rise of 35 degrees C. The requirement for materials less than 300 kilograms per meters cubed density is therefore less onerous when relying on Part 11 test. It's worth noting that insulation materials are often foam-based and may well have a density less than 300 kilograms per meters cubed. For example, the density of phenolic foam and PIR, the insulation used on Grenfell, may have a density of around 35 kilograms per meters cubed. However, a material of limited combustibility is also referenced for another component of the external wall, and this is a complex matter which I will try to explain carefully. In Table A7, up at row 6, marked in blue here on the left, there is a general row which states Class 0 materials meeting the provisions in Appendix A, paragraph 13A. There, at Appendix A, paragraph 13A, it defines Class 0 as the highest national product performance classification for lining materials. This is achieved if a material or the surface of a composite product is one of two performances set. The first being composed throughout of materials of limited combustibility. Therefore, those materials must comply with the limit set in Table A7, and this is done by means of the Part 4 or Part 11 tests also. Again, it is essential to be very aware this is not part of the insulation row below, highlighted in the orange box, and I will come back to this matter again later. I want to now explain how approved document B refers to the classes 1, 2, 3 and 4, as calculated in the Part 7 surface spread of flame test. Classes 1 to 4 are surface spread of flame classifications, and these are defined within Part 7 itself. It's not referred to again in approved document B. The resultant class is simply a measure of how far along the specimen the flame spreads horizontally over 2 time steps. Of the 4 classes, class 1 is the highest and 4 is the lowest. This means the flame travels the least horizontally along the surface when a material is a class 1, and it travels the furthest along the surface on a class 4 material. The 1.5 minute measurement assesses the initial flaming, so how quickly the material reacts immediately after it is exposed to high temperatures. The final spread of flame, shown on the screen also, assesses how effectively the flame is sustained and can propagate along the surface. The flame spread must be within both limits set for a class to achieve that class. I will now explain class 0. So class 0 is defined at paragraph 13 of Appendix A. It is stated as the highest national product performance classification for lining materials, and it is given 2 definitions as described in approved document B. First, as shown in the orange box A, it is a product composed throughout of materials of limited combustibility, as I explained earlier. But there is a second definition relying both on the Part 6 Fire Propagation Index and Part 7, the Surface Spread of Flame Test, as shown in the blue box. Class 1 is obtained from Part 7, and the Fire Propagation Index and Sub-Index is obtained from Part 6. Remember the calculations for the indices in Part 6 and how they are calculated from the gas temperatures measured in the chimney above the furnace, as shown on the screen now. 2 temperature time curves are produced during the test. The upper dark blue line on screen now is an example of the temperature measurement for a combustible specimen. The lower light blue line on screen now is an example of the temperature measurement for the known non-combustible specimen tested as a benchmark in Part 6. From the graph of temperature versus time, 3 distinct time periods are then considered. From 0.5 to 3 minutes, where the difference in temperature is calculated at 0.5 minute intervals. From 4 minutes to 10 minutes, where the difference in temperature is calculated at 1 minute intervals. And from 12 minutes to 20 minutes, where the difference in temperature is calculated at 2 minute intervals. These values are then used in the formulae shown on the screen now to obtain S1, S2 and S3. The calculated S1, S2 and S3 values are then averaged to obtain little I1, 2 and 3, where I is then the sum of these sub-indices. Please now look again at the definition of class 0 on the screen marked in yellow. There it states for class 0, the fire propagation index must be not more than 12, and sub-index little I1 must be not more than 6. And so the test results from Part 6 on a material or composite product must fall within these limits. Additionally, the class value of 1 must be achieved when the same product is tested to Part 7. Class 1 means the flame must not spread more than 165 millimetres from the heated end after 1.5 minutes into the test. But in Class 1, it must not also exceed this limit for the entire duration of the test for up to 10 minutes. And I have shown you where Class 1 is located most closely to the radiant panel shown on the screen now. Because the fact that 2 test result types form the definition of Class 0 is so regularly ignored, with the surface spread of flame test mostly only referred to when discussing Class 0, I think it's important I repeat this point again, that the Class 0 material must be tested to achieve Class 1 and tested again to determine its fire propagation index and to fall under the limits set in approved document B. Crucially, regarding the external wall at Grenfell Tower, Class 0 is also referred to within diagram 40, which presents the provisions for external surfaces or walls. Taking Grenfell Tower as the building example, the external surface classification was Class 0 for the building because it had a dimension over 18 metres and it was 1,000 millimetres more from the relevant boundary to adjacent buildings, and this applied to the part of the building over 18 metres. See the dark grey shading on the right-hand side highlighted in yellow. This meant the composite product used for the external surface needed to have been tested to Part 7, the surface spread of flame, and to achieve Class 1 in that test, and tested to Part 6 and achieve a fire propagation index I not more than 12 and sub-index little I1 not more than 6. Exactly as set out on the right-hand side of diagram 40, marked in the upper blue box. Some important points I suggest to the inquiry panel to note. I have shown so far today that both Part 6 and Part 7 tests can incorporate a composite specimen. I have shown both tests do not directly heat the cut edge of the specimen. I've also shown that the scope of Part 6 states it is for internal walls and ceilings. The scope of Part 7 states it is for walls and ceilings and that it measures horizontal flame spread. And I have shown Class 0 is referred to as the highest national product performance classification for lining materials. But I have also shown it clearly referenced from this diagram 40 for external surfaces or walls, for the purpose of exactly as written in the guidance. This is in order to reduce the surface's susceptibility to ignition from an external source and to reduce the danger from fire spread up the external face of the building. Some final points about Class 0 due to its significance to the work of this inquiry. So I now want to set out how long Class 0 and the two tests upon which it relies, Part 6 and Part 7, have been referred to as the fire safety performance class for external walls in England and Wales. The first national building regulations in England were the Building Regulations 1965. Prior to this, individual local authorities set their own performance requirements through local bylaws. London retained their own bylaws until 1985. In 1965, the external wall construction was not to include any combustible material except specific internal linings or specific external cladding. The cladding is explained later on in Regulation E7 at Part 3B, shown on screen now. It required cladding on any external wall more than 3 feet from the boundary in a building greater than 50 feet in height to have a surface complying with the requirements for Class 0. Class 0 at that time was defined by prescribed construction typologies and with the only test referenced, the surface spread of flame test as existed in 1953. The table on screen now shows the changes in external wall requirements as defined in the National Building Regulations and then subsequently in Approved Document B through time. In the following slides, I have provided all of the supporting fire performance requirements and national definitions from 1965 up to the night of the fire. I will not go through each one in detail, but instead I will point out some significant changes, and that font is marked in blue. This is 1965 as I have just summarised. In 1972, the external cladding above 15 metres was still required to achieve Class 0. However, the definition was changed this year to refer to the newly introduced Part 6 test. In 1976, external cladding above 15 metres was still required to achieve Class 0. However, the definition of Class 0 was changed again this year to refer to both Part 6 and Part 7 tests. In 1985, the fire performance for the external wall performance was dropped down from non-combustible to constructed of materials of limited combustibility, and the Part 11 test standard was introduced. There were some changes too to Class 0, and I will explain these later. In 1992, for the first time, a separate external wall surface. The insulation performance standard was a material of limited combustibility. The definition of high-rise increased from 15 to 20 metres. In 2000, an alternative for the external surface only was introduced by means of a BRE Fire Note number 9, with the insulation performance limits now set only for a ventilated cavity. The definition of high-rise was also lowered to 18 metres. In 2002, the European classification system was introduced as an alternative to the national classes. In 2006, an alternative approach for the whole performance of the external wall was introduced by means of BR 135, and the insulation definition changed again, as shown on the slide. This has remained the case until 2013. I have shown how Class 0 has been referred to in the building regulations and then the statutory design guidance for that time period. It's important for the panel to understand the primary changes to the definition of Class 0 in that time period also. Class 0 was originally based on a surface spread of flame test only from the 1953 test standard, but it was also defined in 3 different ways: either non-combustible throughout, or a material with a non-combustible background and a specific tested fire performance of the surface, or a material with a combustible background but with a non-combustible face. Note the careful distinction between substrate and surface. There were a few changes in the 1972 building regulations. Part 6, the fire propagation test, had been created by the BRE in 1968 after they had identified that the highest classification, Class 1, from the surface spread of flame test could not differentiate between different combustible linings. The definition of Class 0 reference was therefore changed to refer to Part 6 only. The combustible substrate with a non-combustible surface definition was dropped, leaving 2 options for the definition of Class 0 instead of 3. Again, constructed as non-combustible throughout was retained, and the second option, as shown on the screen now, relying on the Part 6 test. This changed again in 1976, when the definition of Class 0 became defined based on both Part 6 and Part 7, and this combination of tests has been relied on ever since. The 2 distinct definitions for Class 0 remained: either constructed throughout with non-combustible materials or a surface tested with a substrate, as shown on the slide. However, in 1985, the definition of Class 0 was significantly changed. First, the definition stopped relying on non-combustible materials, and instead a Class 0 material or surface of a composite product could be composed throughout of materials of limited combustibility, a lower standard. Secondly, the requirement to consider the substrate with the surface was removed from the text in the statutory guidance document. This remained the definition to the time of the Grenfell fire. During the primary refurbishment works, the national class standards were relevant. These were first referring to Section 12 of Approved Document B, in accordance with external surfaces at Section 12.6. The external surfaces of walls should meet the provisions in Diagram 40, and there the national class note is cited as I have explained. And for insulation materials and products at Section 12.7, in a building with a storey 18 metres or more above ground level, any insulation product, filler material, not including gaskets, sealants and similar, etc., used in the external wall construction should be of limited combustibility. The Celotex FR5000, RS5000 and the Kingspan K15 insulation were presented as achieving national class naught. They were not presented as the required material of limited combustibility. ADB in Table A7 for materials of limited combustibility at row 8 for insulation makes no reference to class naught. The Arconic Renobond panels were also presented as achieving a national class on their BBA agrément certificate, which stated behaviour in relation to fire. In relation to the building regulations for reaction to fire, the panels may be regarded as having a class naught surface. This certificate then goes on to state at 6.2, if you look at that on the screen, a fire retardant sample of the product with a metallic grey PVDF finish, when tested in accordance with Part 6, achieved a fire propagation index I of 0, and when tested in accordance with Part 7, achieved a Class 1 surface spread of flame. It goes on to state at 6.3, as a consequence of Section 6.1, which I will explain later, and Section 6.2, as shown on the screen now, the products may be regarded as having a Class 0 surface in relation to the approved document B of the Building Regulations 2000. I wanted to show you the test results from the test report upon which the BBA relied. There you can see the fire propagation index is recorded as 1 and the sub-index little I1 as 0. And that concludes my section of the presentation on the national classes and classifications.
Thank you.
Just going to do a short pause. Okay, I will now explain the European reaction to fire tests. It is useful to note that some of the test methods are similar to those relied upon in the national class system, and others are very different. Also, there's a dedicated classification process presented in a bespoke classification standard. Therefore, the European system does not rely on definitions within the statutory guidance document as occurs for the national classes. I'm going to explain 4 European test standards. Unlike the British tests, which all sit within the 476 series of tests, the European reaction to fire tests each have their own unique numbering, as does the associated classification standard, which is called BSEN 13501 Part 1. First, I will explain each of the 4 tests, and then I will explain the classification standard. The European reaction to fire standards are issued by CEN. This is the European Committee for Standardisation. It is an association that brings together the national standardisation bodies of 34 European countries. CEN is made up of a series of committees and subcommittees that issue standards. The overarching technical committee for fire safety is CEN/TC127, Fire Safety in Buildings. The subcommittee that is responsible for reaction to fire is called Working Group 4, and I have provided the references on the slide for the record. Unlike the British standards, the industry government bodies that draft the European standards are not listed within it. Based on information available on the CEN website, the chairperson of the overarching technical committee for fire safety in buildings is listed as Dr. Debbie Smith, a director at BRE, and the convener of Working Group 4 is a Mr. Roy Veghurst, head of regulatory affairs at Kingspan. Before I introduce the European reaction to fire test standards, I want to highlight this quote from Birgit Messerschmidt, an employee of Rockwell International in Denmark, at the time she gave a presentation at the Fire Seat Conference at Edinburgh University in 2008. She raised the issue of a new reference standard for externally applied products and stated the work to define a new test method for facades had been transferred to EOTA. Again, I've provided the references on the slides. EOTA is the European Organisation for Technical Assessment in the area of construction products, and it is based in Brussels. There are 8 companies listed in the UK membership area, including the BRE, the BBA, and Exova Warrington Fire. There are 4 European reaction to fire tests referenced by the classification standard for construction products. Each part addresses a different element of contribution in a fire. BSEN ISO 1182 is a test of non-combustibility for materials. BSEN ISO 1716 is a test to determine the gross heat of combustion in a bomb calorimeter. BSEN 13823 tests how a specimen reacts when exposed to thermal attack by a single burning item in the corner of a room. And finally, BSEN ISO 11925/2 measures the extent of vertical fire spread and production of flaming droplets and particles when a specimen is exposed to a single flame source for a defined period of time only. The first European reaction to fire test I will describe is the non-combustibility test. The 2010 version was relevant during the Grenfell Tower refurbishment. It is cited as the fifth edition of the standard, cancelling and replacing the 4th edition before it. This test is used for determining the non-combustibility performance under specified conditions of homogeneous products and substantial components of non-homogeneous products. The test apparatus is very similar to that used in BS 476 Part 11, as it comprises an electric furnace capable of maintaining a steady temperature of 750 degrees C. In the European test, the thermocouples are used to measure the temperature within the furnace. A specimen thermocouple can be added optionally, and it is not subsequently used in the classification. 5 cylindrical specimens are prepared, each with a diameter of 45 millimetres and a height of 50 millimetres. They are tested individually, but data is required from all 5 specimens to determine the final test result. If the thickness of the material is different to 50 mil, specimens may be layered and then secured with steel wires, or the material thickness may be adjusted. Tom is now holding up examples of these specimens for the European test. Prior to the test, specimens are conditioned and each specimen is weighed and its mass recorded. I'm showing a video of this test now. As you can see, very detailed requirements are set out for the temperature measurements in this test. The initial temperature, the maximum temperature, and the final temperature, as well as the specimen centre thermocouple and the final specimen centre thermocouple. So a lot of data is produced in this test. The test report has to include a general description of the product tested, including the density, mass per unit area, and thickness, together with the form of construction of the test specimen, and the statement that the test results relate to the behaviour of the test specimens of a product under the particular conditions of the test. They are not intended to be the sole criterion for assessing the potential fire hazard of the product in use. So the same statement again. The second European reaction to fire test I will describe is BSEN ISO 1716, determination of the gross heat of combustion. Heat of combustion is defined as the thermal energy produced by combustion of a unit mass of a given substance. Gross heat of combustion is the heat of combustion of a substance when the combustion is complete and any produced water is entirely condensed under specified conditions. This test specifies a method for determining the gross heat of combustion in a rig called a bomb calorimeter. The version dated 2010 was the version relevant during the refurbishment, and it is cited as the 4th edition of this test standard. The image on screen now shows the bomb calorimeter apparatus. There are two main components, the bomb and the calorimeter. The bomb is a watertight vessel and contains pure oxygen. The bomb is contained within a larger enclosure which is filled with water. When the specimen is burnt in the inner watertight vessel, it releases heat which is transferred through the walls of the vessel into the water surrounding it, and in doing so heats up the water. The increase in water temperature is measured using a thermometer, and a stirrer driven by a constant speed motor is placed in the calorimeter. "50 grams of the specimen is taken and ground into a fine powder. Tom is now holding up a small bag of 50 grams of ground polyethylene. .5 grams of the specimen is placed in a crucible along with 0.5 grams of benzoic acid. This is to assist the sample to combust. This crucible is just a non-combustible holder that is used to store the material within the bomb. The specimen is not directly exposed to flame, but a firing wire is inserted into the crucible holder. When an electrical current is passed through this wire, the material is ignited and the temperatures begin to rise. It's important to note that metal powders are not suitable for use in the bomb calorimeter, as they represent an explosion hazard due to overpressures created within the test vessel. Therefore, where metallic components are present within a composite material, their gross heat of combustion is deemed to be 0 and no test is required. I will show you a video of this test now. So again, very detailed activities are required as defined in the test standard. 3.5 gram specimens are tested, and the gross heat of combustion for each is then calculated based on the increase in temperature of the water. This can be done as it is a scientific constant that it takes 4,184 joules of heat energy to heat 1 kilogram of water by 1 degree. As the quantity of water in the calorimeter is a known value, the amount of energy it took to heat up can be back calculated. The average of the 3 specimen results is taken, and the final result is given in units of joules or megajoules. To be a valid test, the results must comply with the criteria shown in Table 1 on the slide. The test report has to include the information as I have shown on the screen, including the similar statement I've referred to a few times this morning. The third European reaction to fire test I will now describe is known as the single burning item test. This British standard is the UK implementation of a European norm, and the 2014 version was relevant to the Grenfell Tower refurbishment. It superseded a 2010 version, which was withdrawn. In the single burning item test, a specimen forming a corner is tested. Tom is now standing to an exact to-scale replica of the BSEN 13823 single burning item test specimen. The specimen holder is a metal frame with a calcium silicate board facing called the backing board. The specimen to be tested is then fixed onto the backing board according to the fixing conditions in the end-use application required. The specimen holder comprises 2 wings, designated a short and a long wing. It is the largest specimen used in any of the reaction to fire tests in either Europe or nationally. The long wing has a length of 1 metre and a height of 1.5 metres. The short wing has a height of 1.5 metres but a shorter length of 495 millimetres. The maximum depth or thickness of the total specimen tested in the single burning item test is 200 millimetres. Specimens with a normal thickness greater than 200 millimetres are again cut away from the unexposed side so they fit into the test rig. Materials with a thickness less than 200 millimetres are tested at their normal thickness with no requirement for scaling up. A total of 3 specimens are tested, and both long and short wings must be replaced after each test run. The single burning item test also refers to further information about how the specimen is mounted in its end-use application, including the presence of substrates. These are products used immediately beneath the product about which information is required. The single burning item test standard sets out clear guidance regarding the issue of mounting and substrates. This is the test upon which Arconic relied regarding Renobond products. When products are tested and mounted as in their end-use applications, the test results are then valid only for that application. When products are tested using a standard mounting, additional guidance is provided. For example, boards in the end-use application of a ventilated cavity behind it shall be tested with a cavity of at least 40 millimetres. Boards to be mechanically fixed to a substrate in their end use should be test fixed to a substrate using appropriate fixings. And products that in their end use application are glued to a substrate shall be tested glued to a substrate. The test rig contains 2 burners, a primary burner, as is shown in the diagram, and an auxiliary burner, and I will explain that next. This primary burner is located at the corner of the two wings, offset from the front face by 40 millimetres. It is a triangular tray filled with sand with two equal sides of 250 millimetres and a height of 80 millimetres. A gas pipe is attached to the tray, so the gas flows through the sand, diffusing it. The burner is calibrated to give a heat output of 30.7 kilowatts, which is intended to represent a waste paper bin on fire in the corner of the room. Although the burner is offset from the front face, flames given off by the burner can make direct contact with the outside face of the test material. The auxiliary burner is located remote from the test apparatus on a post opposite to the specimen corner and at a height of 1.45 metres from the floor. The auxiliary burner is ignited with the same propane gas supply as the primary burner, but simply to provide a baseline average burner heat and smoke output at the start of the test. In order to subtract the contribution of the primary burner from the measured results at the end of the test, and to carry out calculations with the results and attribute them only to the specimen, the only purpose of the auxiliary burner is to run it for a period of 180 seconds before the primary burner is ignited, and then subtract those values from the total heat and smoke output of the burner and specimen at the end of the main test. An exhaust system is located above the test apparatus. In addition to the practical purpose of extracting smoke from a burning specimen, several measurements are taken in the duct exhausting the smoke. These are thermocouples to measure the temperature of the smoke, a pressure sensing probe to measure the flow-induced pressure difference in the duct, a gas sensor that measures the oxygen and carbon dioxide content of the air being extracted, and a light source and light sensor that shines through the smoke to measure how much light is being blocked, hence how dense the smoke is. The video on screen now shows the test procedure for the single burning item test. So again, there are very detailed sets of requirements for the data to be produced, or for the data to be measured in this test. The horizontal flame spread is recorded as the occurrence of sustained flames reaching the far edge of the long wing specimen. The fall of flaming droplets or particles shall be recorded only within the first 600 seconds of the exposure period, and only when the droplets or particles reach the floor level of the trolley outside the burner zone. After 26 minutes, the gas supply is terminated and the automatic recording is also stopped. And I've explained all the sensors in the exhaust duct These quantities are recorded automatically and used to calculate the volume flow, the heat release rate, and the smoke production rate from the specimen during the test. Section 9 of the standard sets out how the results of this test must be expressed. There is a lot of data and analysis required, and it is essential to read the BSEN in full to understand this. These are key to the European classes. In short, the burning behaviour is represented by a series of graphs showing the average heat release rate, the total heat release rate, and the fire growth rate indices versus time. The smoke production behaviour is given as a further series of graphs of the average smoke production, the total smoke production, and the smoke growth rate index. Later in the classification standard, the designation s will appear, and it is calculated here. The production of flaming droplets and particles must be confirmed as an occurrence or not for the product. Later in the classification, the designation d will appear, and it is calculated here. On the slide now are the requirements to be included in the test report. Again, a general description of the product tested, including its density, mass, form of construction, description of the substrate, and fixing to the substrate must be recorded. And again, that statement regarding the test results. Annex A of this standard goes on to set out in detail the series of parameters that must be calculated to evaluate the performance of the product. I've marked only some of them in yellow here. These include the total heat release rate noted as THR on the screen, and the fire growth rate indices noted as FIGRA values on the screen. But all of the calculations listed here must be carried out using the test data. The standard provides a detailed calculation method for THR 600S, which I have shown on the screen now. I am not going to talk through these equations today, but instead it's to note that THR 600S is defined as the total heat release rate of the specimen in the first 600 seconds of the exposure period. The standard provides a calculation method for FIGRA, which I have shown on screen now, and again, I'm not going to talk through these equations today. FIGRA also has a very complex definition, which I've presented on the screen here, and I will come back to that again later. It is a little easier to understand the data analysis by observing here how the results are then presented in a test report. On screen now are the heat release rate versus time, THR and FIGRA graphs for the Arconic Renobond 55PE riveted panel. Ultimately, as I've presented already, Section 9 of the test standard sets out exactly how the results of the test must be expressed. And all the calculations I have shown result in this required expression, as shown again on the screen here. These results are referred to for nearly every European class. So despite their complexity, an awareness of them helps in understanding the European classifications later in my presentation. Finally, the fourth European reaction to fire test is BSEN ISO 11925 Part 2, the ignitability of building products subjected to direct impingement of flame. This is referred to as the European Single Flame Source Test. It is designed to simulate a small flame being directly applied to the surface or to the edge of a material. The standard is dated 2010 as the version relevant to the Grenfell Tower refurbishment. It superseded a version dated 2002, which was withdrawn. On screen now is the apparatus for the single flame source test. The apparatus comprises of a Bunsen burner housed within an outer housing called the combustion chamber. The image on screen now shows a cross-section through the combustion chamber, looking side on. The sample is suspended from the back wall of the outer housing, and the Bunsen burner is mounted onto a horizontal plate so that it moves smoothly forwards and backwards in a horizontal plane along the centre line of the combustion chamber. An aluminium tray containing sheets of paper is placed below the sample so that any flaming droplets will land on the paper and potentially ignite the paper. A test specimen 250 millimetres long by 90 millimetres wide is prepared. The maximum permitted thickness of the specimen is 60 millimetres. A material that is normally less than 60 millimetres can therefore be tested to its full thickness, and a material that is greater than 60 millimetres should be cut down from the unexposed side to fit into the test rig. Tom is now holding up a 2-scale replica of the test specimen. As stated on the screen, a total of 6 representative specimens are required in one test. Another key point is if a product is installed with covered edges, but can also be used with unprotected edges, tests shall be performed on both covered and uncovered specimens. This is different to Part 6 and Part 7 discussed earlier, where the tests are designed to prevent edge exposure. Again, the issue of incorporating the influence of the substrate on the specimen behaviour is addressed clearly in the standard. The specimen is vertically mounted into the test frame. A burner is fitted on a track and applies a flame directly to the surface of the material. This burner uses a propane gas fuel, and the flame length must be calibrated to be no longer than 20 millimetres. You can see in the diagram on the left that the flame is angled at 45 degrees. 2 different exposures are used: surface exposure and edge exposure. A surface exposure test must always be undertaken. Edge exposure tests are only undertaken if the edges can be exposed under end conditions. Therefore, if in the envisaged end-use application, direct flame attack on the edge cannot occur, the product does not need to be tested. When a surface exposure is used, the flame is applied 40 millimetres up from the bottom of the specimen on its front face. A reference line is marked on the sample, and I will show you this on the next slide. When an edge exposure is used, the flame is applied on the bottom edge of the specimen. The flame is then applied to the material for either 15 or 30 seconds, depending on the classification the sponsor wishes to obtain. The higher European Class B down to the European Class D are based on a 30-second exposure. Once the flame is applied, the extent of vertical flame spread is observed and recorded. The image here is from a test video that we'll watch in a few moments. The bottom blue line is the 40 millimetre line where the flame is applied for a surface exposure test, and the second line marks 150 millimetres above the flame application point. If the flame application time is 15 seconds, then the end of test is 20 seconds to allow 5 seconds of observation time. If the flame application time is 30 seconds, then the end of test is at 60 seconds, allowing a further 30 seconds observation time. For the edge exposure version of the test, the burner has specific required locations set out in the test standard. For a material greater than 3 millimetres thick but less than 10 millimetres, the flame is applied to the underside using the 45-degree angled burner 1.5 millimetres behind the front face of the specimen. This is whether it's a single layer, as shown by the image on the left, or multiple layers, as shown in the figure on the right. Where the material is less than 3 millimetres thick, the flame is applied at the midpoint of the bottom edge as shown in the test standard. For all multi-layered products greater than 10 millimetres, an additional set of tests shall be carried out, with the specimen turned at 90 degrees round its vertical axis and the flame impinging at the bottom edge of the centre line of each different layer. A test is done for each of the layers that make up the sample. I'm now showing you a video of this test procedure. Regarding the results, first it is noted whether the flame extent reaches the 150 millimetre line marked on the screen. Also, the presence of any flaming on the specimen once the pilot flame is removed is recorded. The test report must identify whether any flaming debris falling from the specimen ignites the filter paper. On the slide now are the requirements for the test report. The results of the test shall be expressed by a record of the following: the position of flame application, whether ignition occurs, whether the flame tip reaches 150 millimetres above the flame application point, and the time at which this occurs. Presence of flaming droplets or particles which cause ignition of the filter paper, and observations of physical behaviour of the test specimen. Again, the test report has to include a general description of product tested, the form of construction of the specimen, including the description of substrate used and methods of fixing. This test also requires information on the intended application of the product, if known. And it contains the same statement again. To finish this session, finally, when I was explaining the single burning item test earlier, the large-scale specimen heated in the corner, I mentioned that smoke production and flaming droplets were recorded in that test. I have also explained that flaming droplets are recorded in this last test, the single flame source test. In the classification standard, which I'm about to explain, it sets limits for little s and little d. As shown on the screen, it is useful to understand the smoke production is obtained from the single burning corner test only, whereas the flaming droplet performance is obtained from both the single burning item and single flame source test. This ends my description of the detailed test procedures presented in the 4 European reaction to fire test standards.
Good, thank you very much indeed.
Mr. Chairman, I think that's the moment that we were going to take lunch.
Yes.
So we're in your hands. We could either take around an hour and begin again at 1:45, or just to be aware, I think there's around an hour's worth of presentation left.
Probably just under an hour.
Just under an hour left. So equally, we could break now and start again at 2.
I'm going to ask Dr. Lane what she'd prefer to do.
I think that I'm communicating an extensive quantity of information, so maybe we should wait till 2.
I'm very happy to do that.
If you're happy to do that. Yeah.
This turn is
Yeah.
as well.
Yeah.
Right, well, we'll stop at that point and then resume at 2 o'clock.
Okay.
All right?
Thank you.
Thank you very much. Yes, thank you. 2
Thank you
o'clock,
very
please.
much. Thanks.